Unit Operation Classroom, which is an initiative of unitoperation.com. We are now discussing GATE 2024 question 62 problem. A chemostat with cell recycle is shown in the figure. So this is my chemostat. What is a chemostat? Chemostat is a CSTR where microorganisms multiply using substrate. In this particular case, this is glucose. So what happens? You have cells here in this chemostat, and they consume glucose, which is a substrate, and a lot of times there are nutrients, which is not mentioned in this problem. So these cells consume the substrate, which is their food, to create more cells. Okay, and uh, here we have a diagram here. Let me quickly explain what is in this diagram. So this is my chemostat, and this is the feed, and CC represents the cell concentration, and CS represents the substrate concentration. Uh, Initially, CC, it is a sterile. That means there is no cell here. This is a sterile, but there's a certain substrate concentration. That means the glucose concentration in the feed, which is given to the reactor. So this is a CSTR. And what happens, there is at steady state, of course, there are already some microorganisms which consume this glucose, and they are converted, and in turn they use that as a food and they multiply. So part of this content of this chemostat is taken out. We'll discuss what this alpha is, and then what happens is a cell concentrator. In the cell concentrator, what happens? There is a differentiation in the cells, and of course, if a stream is continuously taken out from the cell concentrator, whose flow rate, of course, at steady state will remain the same as the inlet flow rate, because if you just do like this, so the inlet flow rate must be the outlet flow rate. Okay, so and this is the concentration of the cells in the outlet stream, and this is the concentration of the substrate in the outlet stream, and part of that flow rate is taken out and put it back, because this contains some important cells which get acclimatized with this particular substrate, which is glucose. So always there is a recycle of of the effluent from the chemostat, and we let's call that as alpha F, and the concentration of the cell in this one is, let's say, beta CC1, and this is, of course, the glucose or the substrate concentration, of course, remain the same here. Okay, because here only the cells are concentrated and taken out. All right. So you can see that if this is my F, and this alpha F is continuously, this is the flow rate, alpha F is continuously added. So the total flow rate that's going out is 1 plus alpha F. Okay. And this is the CC1 and CS1 concentrations of the cells and the substrate coming out of the reactor, or in this case, this is chemostat. And CS1 concentration, of course, remains the same, because this cell concentration does not do anything with the glucose concentration. It just concentrates the cell. So CC2 is the changed concentration of the cell, which is going out. And again here, the glucose concentration remains the same. And beta CC1 means after cell concentration, this is the concentration of the cell which is remaining here, and that is put it back. So this is basically the structure of this problem. Assume monode kinetics with specific cell growth. So the monode kinetics is a very standard kinetics, and you can look into it in any textbook, Levenspiel or Faulkner, and we know mu g is a specific growth rate at a specific substrate concentration. This is my mu g. And mu m is the maximum specific growth rate, which is like here, this one here. And of course, this growth rate is defined as this one. Ks is called the substrate concentration at which the microbial growth rate reaches half of its maximum value. Why it is half? Again, you have to read the textbooks. And of course, CS is the substrate concentration, which is the glucose concentration. And the value of mu n and the Ks are already given for this particular system. Assume maintenance and death rates are to be zero. Okay. Input feed to be sterile, so there is no cell coming in from the feed stream, and at steady state operation, the glucose concentration there is cycle stream, so which is here and here. We have to calculate that. Uh, Few problems of this type have already been discussed in Faulkner, so you can look into it. So now let's look into the problem in little more detail. As we said, feed is sterile, so CC0 is equal to 0, and CSO is of course a concentration, which is the substrate concentration, which is the glucose in this case in the feed. Okay, and the actual reaction, let's look at it this way: cells which are already here plus glucose, which is the substrate here, creates more cells here. Okay, let's do the cell balance over the concentrator. So we are doing the cell balance over this concentrator here. So here it is 1 plus alpha F, which is the flow rate coming out from here, 1 plus alpha F into CC1, which is the concentration of the cell coming out from the reactor, is equal to FCC2, which is going out from here, plus alpha F, which is this one, multiplied by beta CC1, which is the concentration. We are doing the cell balance. So these F's, of course, cancel out here, and we get the CC2 in this is the form. And we already know the values of alpha, and beta, which are already given here in the problem. If we do that, so we get CC2 is equal to 0.5 CC1. All these things are given in the website here. Okay, so basically CC2, which is this one, is going to be equal to half of CC1. So that's what the calculation says. Now let's do the cell balance on the chemostat. So on this chemostat, we do the cell balance. So this big FCC0, the flow rate FCC0, that's what is coming in, but we know CC0 is equal to 0. It's a sterile one, plus alpha F, which is this one, which is coming in into beta CC1. So, which is this one, is equal to, now there is a generation of cells, and that generation of cells is given by the monode kinetics right here, which is mu g into CC1. Of course, the volume has to be multiplied there. So that's what it is. Plus, what is have? Plus, we have 1 plus alpha F, which is going out, F CC1. Okay. 1 plus alpha F CC1. So if we do that, we get the value of mu g as F, this particular value. Do the calculation, we know the values of alpha and beta, we get this calculation here. Now let's connect this mu g with the monode kinetics, which is already given. Value of mu m and Ks are already given in this problem here. Value of mu m and Ks are already given. So if we do the calculation, we get CS1 is equal to 3.0 gram per liter. So the concentration of glucose in this stream, that's what they want to find out. CS1, concentration of glucose in the recycled stream, is equal to 3 grams per liter. So that is my answer. Okay. Now let's quickly look into the application of this problem. This problem is symbolic, or it is a very good example of a very important process in chemical process industries. We know that activated sludge process is a very widely used in different process industries. So let's say this is a wastewater influent coming in. There's a preliminary treatment, particles, grades, etc., which are removed first, and then it goes to a primary clarifier. And from the primary clarifier, of course, some primary sludge is taken out. Now here, so this of course from here in the chemostat, this feed of course is this one here, wastewater influent, which is coming in. Now the chemostat here is of course this aeration tank, where here this is microbial microbes here. So these are the microbes which take in the substrate, in this case the pollutants, and they degrade and consume, and they convert that into convert that into harmless products. So the cells in the chemostat here, cells in the chemostat are the same as the biomass in the aeration tank. And air is supplied, and there will be, of course, some amount of nutrients here for proper application of the aeration tank. Then from here, the wastewater is taken to a secondary clarifier. In the secondary clarifier, the sludge comes out from here. So basically, this is the sludge, waste activated sludge, which is comes out from there. A part of the stream is taken out and put back here. So this is the recycle stream containing part of the microbes, because this contains those microbes which are already activated and acclimatized to this pollutant. So this is a very important one. They don't waste totally, so they put it a part of that into the aeration tank here. So the same thing here in the cell concentration. So part of that is put in here. Okay, and the fluoride which comes out from here, that is then put to a disinfectant, and the final effluent, which is basically this one right here. So this problem is a very good example of a very big industrial and a very, very, very widely accepted industrial problem.